Good afternoon. My name is Joseph Namogo. I'm a student at the University of Florida College of Engineering, and today I'm going to present a paper on the linearity analysis of CMOS for RF applications, authored by Sanghoon, Kang, Byounggi, Choi, and Bumman, Kim. Linearity analysis for RF applications. The linearity of CMOS is analyzed. Transconductance and output conductance are two dominant nonlinear sources of CMOS. Capacitances and substrate leakage networks do not generate any significant distortion, but they reduce the output impedance for the best linearity and the power gain at a high frequency, and the output conductance nonlinearity is significant at a high frequency, up to 50 gigahertz. The output conductance is the dominant nonlinear source, and at a higher frequency, the transconductance is the dominant nonlinearity source. OIP3 is reduced by the effects of those components. OIP3 are calculated for various gate length processes. CMOS linearity is dependent only on current density and drain bias voltage, but is not dependent on gate length. Introduction. So there's a tremendous interest in using CMOS technology for RF and microwave applications, and many CMOS models for RF applications are proposed. Most of the models are focused on small signal characteristics such as small signal gain and noise trigger. Recently, many researchers have studied about output power, efficiency, and coupling to other components. These are well-known disadvantages of CMOS process, and various efforts have been made to overcome these disadvantages for successful CMOS RF IC implementation. However, linearity is always one of the most important issues for RF circuit. Some works consider only the transconductance of CMOS linearity analysis. For a short gate CMOS, the output conductance becomes an important nonlinear source and must be considered in CMOS linearity analysis. In this work, CMOS output conductance nonlinearity is analyzed and compared with transconductance nonlinearity. The linearity trend with downscale device is also shown in section 2. Capacitance effects is discussed at section 3, substrate leakage network, and its effects are analyzed in section 4. Transconductance and output conductance nonlinearities. Taylor series are made simple and are widely used for nonlinearity analysis. Drain current in Taylor series is expressed as shown in 1. These terms are obtained by simple measurement at low frequency. Assuming drain is shorted at signal frequency, all output conductances GD, GD2, GD3, and cross-modulation terms GMD, G2D, GMD are cancelled, and only transconductance terms GM, GM2, GM3 remain. Third order intercept point IP3 of gate voltage amplitude given by equation 2 has been used as a device nonlinearity criterion in many works. Now, this model is not accurate enough to compare output conductance nonlinearity to transconductance nonlinearity. The output nonlinear currents from the components are calculated. In this approximation, third order intermodulation currents caused by the transconductance and output conductance nonlinearities are given by equation 3 and 4. I sub IM3 trans and I sub IM3 conductance. A is the fundamental voltage frequency, fundamental voltage amplitude at the gate. VDS is the fundamental voltage at the drain expressed as VDS GMA over G load plus GB. transconductance and output conductance nonlinearities. TSMC 0.25 micrometer by 10 micrometer CMOS BSIM3 model is used for the study. Multi-LCS parameters are extracted from the DCIV curve of the model. Using these parameters and equation 55, the output third-order intermodulation curve for various impedances are calculated and compared with harmonic balance simulation. The result of this is shown here in figure 1. As shown, the nonlinear currents are dependent on the load. So you can see the nonlinear currents are dependent on the load. Drain voltage swing is small at low load impedance, and the transconductance nonlinearity dominates the device nonlinearity. At high load impedance, the output conductance dominates the device nonlinearity. Only with GM, GM3, GD, and GD3 coefficients, the calculation result matches the simulation very well. When GMD and L higher components are included, calculations predict the simulation results even better. The effects are small and can be neglected in saturation region, but in linear region, the cross modulation terms are large and should be included in accurate calculation. Now in figure 2, output third-order intercept point OIP3 and power gain are shown for its very own resistance. The maximum OIP3 is obtained at the load impedance less than the value of maximum gain, Z gain. Maximum linearity is achieved at the load impedance where the output conductance nonlinearity increases to the level comparable to the transconductance nonlinearity, GN. Nonlinearity ZLN. After ZLN, the ZLN. After ZLN, the fundamental and intermodulation currents IM3 remain the same. All right. And their powers increase at the same rate, proportional to the load resistance. Thus, OIP3 increases. Fundamental current stays constant up to Z gain, but the intermodulation current due to the output conductance nonlinearity IM3 increases rapidly in this condition. In this region, and OIP3 decreases. Above the gain, power gain both decrease. Above the gain, IM3 and power gain both decrease. If you want a highly nonlinear operation, the output impedance should be reduced from the power maximum impedance. It is desired to select an output load between Z lane and Z gain for good RF performance. Maximum OIP3 for TSMC 0.3 micrometer, 0.2 micrometer, and 0.18. So 0.35 micrometer, 0.25 micrometer, and 0.18 micrometer are evaluated to understand the process-dependent linearity. Total gate width is 100 micrometer with 10 fingers. Linearity varies with output load resistance. The maximum OIP3s and corresponding load impedance for various current levels and drain bias voltages are calculated. As the gate length becomes shorter, the transconductance becomes more linear, but the output conductance becomes more nonlinear. As a result, the overall linearity of CMOS does not change for the gate length variations shown in figure 3. Right. A shorter gate, and you can see them right here. Okay, the gate lengths becoming shorter, but they are more or less the same. They have the same trend. A shorter gate MOSFET delivers a little better linearity at high current density. At lower current density, the same or better linearity is achieved. If IIP3 is considered, a short gate device is more nonlinear at the same input current level. To verify the above conclusions from measured data, 0.18 0.18 micrometer, 0.25 micrometer, NMOS from high-nets are evaluated. VGS IDS curve and VDS IDS curve are measured. GM, GM3, GD, and GD3 are extracted from the measured data. Maximum OIP3s are calculated for various current densities, and bias voltages using equation 3-4 depicted in figure 4. The device output linearity depends only on the current density and bias voltage, not on the gate length. These trends are identical to the simulation results. Previous experimental results show that CMOS input impedance is a major source of nonlinearity at high frequency. The input impedance of CMOS consists of two nonlinear sources, gate source capacitance and feedback component through gate drain capacitance. The effects of CGS on the input impedance nonlinearities are evaluated for various source impedances. To reduce the effect of CDG, drain is shorted and gate voltage is varied by various source impedances. Simulated results in figure 5 shows that the gate voltage intermodulation remains constant, i.e. CGS by itself does not degrade the device linearity up to several gigahertz. The gate drain capacitance is generally neglected for a simple linearity analysis, but it forms a feedback loop for harmonics and disturbs device linearity at a higher frequency. The gate fundamental voltage and intermodulation components for various load impedances are simulated. The harmonic generation by CGD is minimal compared to the other two sources we mentioned. The gate drain capacitance is small and remains almost constant in saturation region, and its effects is negligible. These capacitances do not generate significant harmonics, but modify the harmonics by the feedback through CDG and by reducing output impedance. The output IM3 current modified by these capacitances can be obtained from the following calculation. So it's VD, question 6, VG, question 7, AV, question 8, where AV is a voltage gain from gate to drain. The intermodulation currents are given by question 9, 10, and the Y out is given by equation 11. The drain intermodulation voltage is fed back to the gate through CGD and modifies the intermodulation current. This feedback effect can be calculated as equation 12 and equation 13. The IM3 output current is calculated using these equations and is compared with simulation for various load impedances up to 6 gigahertz. Calculated results shows that GM3 and GD3 are the dominant nonlinear source up to the frequency. At a low frequency, GD3 dominates device nonlinearity, but at a high frequency, the transconductance become more important. For 0.25 micrometer process, transconductance nonlinearity becomes comparable to the output conductance nonlinearity at 4 gigahertz. Above that, the transconductance nonlinearity dominates. Substrate effects on nonlinearity. In the substrate network, the conductance is considered as a constant value, but the source substrate and drain substrate diodes are nonlinear components. These diodes are always reverse biased and function as nonlinear capacitances. Substrate model used for calculation is shown in figure 6. Right, these are the reverse biased diodes. Question 6 to 13 are modified to consider the substrate effect. Calculated results are compared with harmonic balance simulation results as shown in figure 7. There are good agreements between the calculated and simulated results. These are simulations. These are the simulated results. It's difficult to make them out, but the field shapes, that's simulations. And we can see the unfilled shapes of the calculations. Then we can see the transconductance and the output conductance. The load impedance, the load-dependent nonlinearity contributions from the transconductance and output conductance in Figure 7 and OIP3 gain curves are shown in Figure 8. Okay, load gain in OIP3, including substrate network effect. The high frequency Z gain is reduced because the capacitance of Z lane remains constant. CDB adds output capacitance and device gain is reduced. The output voltage swing is reduced and the effect of output conductance becomes less important. When the substrate network is included, the crossover frequency where the transconductance nonlinearity becomes larger than the output conductance nonlinearity is reduced to about 2 GHz, and OIP3 is significantly reduced. At a high frequency, the optimum load impedance for the linearity can be even higher than the power matching impedance. So in conclusion, CMOS linearity has been studied and we found that it is not improved with gate length reduction. Only the increases of current density and drain bias voltage improve the output linearity. The short gate length, CMOS can operate at a high current density and so can deliver a higher linearity. GM3 and GD3 have dominant nonlinear sources for the frequency band study up to 6 GHz. The effects are calculated with simple equations that have been derived. Internal capacitances and substrate networks are also included in the calculation. We have found that those components are not the sources of nonlinearity, but reduce the high frequency gain and the optimal impedance for low distortions. At a high frequency, the transconductance nonlinearity becomes the dominant source and the OIP3 is reduced significantly. The crossover frequency for a 0.25 micrometer MOSFET is around 2 GHz. Thank you.